So I think we can start. Are we ready, Luca? Okay. Thank you for coming. Today we start this cycle of faculty seminars. We will have two of them today, half an hour each. We start with Professor Eugenio Moggi, and we'll listen what he's going to tell us. Thank you.
So I'm going to discuss reachability in the context of hybrid systems. So the structure of the talk will start with reachability and safety in the context of discrete systems. Before moving to the case of hybrid systems, where if you just try to reuse the reachability in the discrete setting in a simple-minded approach, you don't get something safe, you get a naive reachability which is unsafe. But before moving here, I will take a more abstract view. So we'll think of reachability and other kind of analysis as living in a category of complete lattices and monotonic maps. And that give enough space to adjust, to explore different kind of reachability in the context of hybrid system and continuous systems. Actually, the examples that I will use are all very simple rigid body systems, so they are not really complicated or don't have to do with cyber physical, just physical systems. So first of all, let me recall the definition of transition system. It's just a set of states with a transition relation. So the fact that it's a set, it's captured the idea of being discrete. And the transition relation corresponds to one step of evolution in the system. This model is supposed to model a closed system, so it's not just a component, it's a component together with its environment. And the non-determinism is very important because typically you don't know very much about the environment, so you have to accommodate all possible behavior that the environment might have, even if your component is deterministic. But of course, you could use non-determinism also to describe or to decide to avoid certain implementation issues. So it's more like a don't care non-determinism. The other point I'd like to mention is that reachability is a fairly simple kind of analysis that you may want to do on a system, but more complex analysis could be reduced to reachability problem for a different transition system. For example, if you are interested at which step you reach a state, you could just use this transition system where you add a counter, and reachability for that will give you information on when you reach a state in the original system. Now, the definition of reachability is very simple. You have the transition relation, you take the reflexive and transitive closure, and this allows you to define for each set of initial states what are the states reachable in a finite number of steps. So I put F here to stress the fact that there are states reachable in a finite number of steps. And if you have this notion of reachability, you can define safety, provided you decide what states you consider bad. So you can say that the set of initial states is safe if what is reachable does not intersect the set of bad states. So you cannot reach bad states. That's okay. Now I move to more abstract setting where I don't really care about the dynamics of the system. I care about analysis of the system. And so basically I replace the set of states with the power set. but the power set is more than a set, it's a complete lattice. So it's important to consider also the order relation. And the order relation is important mainly because it's a way to express approximation. So I can use the order relation to say, well, some element in a lattice or in a poset, it's approximate another element. So somehow the idea is that I go bigger, so I have more space for choice, for choosing approximations. Another important property of this category is that the notion of approximation can be extended to relate to different complete lattices. So maybe here you have a very big complete lattice like P of S, and here you could choose a finite one. And if the monotonic map here that is supposed to map the small space in the bigger one preserves subs, then you know that there is an adjoint. So somehow you can move between the two partial orders, the one on X and Y, using F and G, and they are related by this if and only if relation. Now I'll give you an example of that. So here you have your analysis that could be the reachability, this RF function I defined before, but it could be any analysis that it's expressed as a monotonic map. When I move from S to P of S, of course, I increase a lot the cardinality. So if I have something countable, I get something uncountable. But then I could choose something finite. So typically in abstract interpretation, you use this trick. You have an analysis that is accurate, but it's impossible to compute, and you can approximate it with an analysis over a finite lattice in this case. It doesn't have to be finite. And the relation that say that this analysis is in this case on the finite poset, it's an approximation is given by the less than or equal relation between this non-commuting diagram actually. And here it's important to have this adjoint to the inclusion that give us for each subset of S the best element in X that approximate it. And so we have a best approximation. And that's the sort of property that you expect. Oh, yes, another point is what is the partial order that I should take on P of S? There are, of course, two options, the inclusion or reverse inclusion. If you think in terms of information, you could say that the smaller, the more precise, and so the better. But you can always turn things upside down. Now let's move to the continuous or hybrid setting. Before doing that, however, let's analyze what are the differences. So first of all, time. So before we use the natural number to model time, now we use the real numbers. States, well, before it was just a set, now it's more reasonable to take something with some topological structure or a metric space or a Euclidean space. So for what I'm doing, it's enough to consider Euclidean spaces. And the other important thing is that when you do observation or test on the system, in a discrete system, things are exact. In a hybrid system, there is some noise in imprecision. So in physics, for example, when you make a measurement, you don't get a real number, you get a number with an error. The other point is when you want to do analysis using a computer, of course, you have other issues that have to do with limitations in computers. And so typically you use floating point to represent real numbers, but actually the more appropriate way of modeling or capturing imprecision is through floating point intervals. more or less in late 60s, there was this approach based on interval arithmetics. Is not really mainstream, but I think it's the right way of doing things with computers. Okay, so now what are the issues when we move to this hybrid setting? And actually here it's enough, all the examples are just examples based on simple mechanical system like balls. So there is instability. For example, if you have a ball sitting on a top of a hill, well, the mathematical model says that it stays there, but of course you know that is more likely to fall somewhere. The other issue is that you can no longer identify what is reachable in finite time with what is reachable in a finite number of transitions. For example, if you have a bouncing ball that loses energy every time it bounces, we know that it will stop after a finite amount of time, but the model tells that it will take infinitely many bounces to stop. Okay? So you cannot identify the fact that something is reachable in a finite number of steps with something is reachable in a finite amount of time, of real time. Okay, so now I move to a model for hybrid systems. So it's a sort of replacement for a transition system. That's something I've just taken from a paper that it's a review paper on hybrid system and control theory. So here you have just two relations, but now they are not just on a set, they are on a Banach space, or you say Euclidean space. Let's think of R of n. Okay? And they have two different interpretations. The flow relation, you have the first element is a state, the second is not really a state, it should be viewed as a velocity. Okay? Of course, in a Banach space, the two things are the same. Instead, in the jump relation, both are states. Now, you can imagine some operations similar to the one I described for a transition system that you can perform on hybrid systems. So, for example, I can add a clock, a real-time clock. Then this tells you that the time will flow at speed 1, right? It's the derivative of time with respect to time. When you jump, so the idea is that when you jump, it takes no time, so it's a reactive system in this case, and so in this case the time stays the same. Of course, you could do something different. Instead of counting or measuring the time, you could count the events. In this case, when you flow, there are no events, so the derivative of this counter with respect to time is 0, but when an event occurs in 0 time, you increase the counter. And of course, if you have some topological structure, like in a Euclidean space, you could perform operations like taking a relation and taking its closure. You can take the closure of F and G. Now, the obvious things to do if you want to define reachability is, well, let's move to the original definition. So let's define a transition system associated to an hybrid system. And that's what I'm doing. So the only difference is that the set of states is not a set, it's a Banach space. But we have a relation. So here I'm going to define not a binary relation, but a time relation. So just for clarifying the different role of F and G. So here I have this D that it's a real positive number, could be also 0, giving you how long the transition is going to take in terms of real time. So if it takes 0 time, it must be a jump. If it takes a non-zero time, it must be a flow. And to flow, what does it mean? It means that you have a continuous function from this closed interval to your space. It must be derivable in the open interval. The derivative must be continuous as well. So top is the category of topological spaces. Doesn't matter. Of course, you should start from S and you should arrive to S prime. And moreover, while you flow, you must respect the flow relation. Okay? So the derivative of H and H at each time must be related by the flow relation. Okay? Of course, this is a generalization of what you do in mathematics, where you consider differential equations. Here, instead of equations, we have inclusions. So we are not saying that the derivative of H prime is equal to something. We say the derivative must be in this set that depends on the point, on the state where we are. Now I would like to talk about noise and robustness, and to do that I will forget for a moment hybrid systems, and I consider a metric space. Of course, a Banach space, Euclidean space, it's a particular kind of metric space. So this is a recap of some topological notion in the setting of metric spaces. So you have an open ball, okay, well known. Then an open set in a metric space is just the union of open balls. A closed set is the complement of an open set. And there is a more direct characterization of the closed sets in a metric space. Namely, you have that C is closed if every sequence in your closed set that has a limit in the space must also contain the limit. Okay? So a closed set is closed with respect to limits. And then we can define a complete lattice of closed subset of a space. Now, it's quite easy to, it is well known that closed sets in any topological space, they are closed with respect to intersections. So that means that we have that this inclusion of closed sets into the complete lattices of arbitrary sets preserves subs that correspond to intersections, and so we have an adjunction in this category of complete lattices and monotonic maps. And the adjunction is given by closure. By the way, if S is a discrete metric space, by that I mean that the value of the distance can either be 0 or 1, then closed sets, every set is closed and also open. Okay, so these notions are not interesting in a discrete setting. Okay, so given any subset of S, you have the closure, which is the smallest closed set containing S. You can generalize the open ball construction with by replacing a point with a set, and this is always open because it's going to be the union of open balls. And moreover, you can consider the closure of this, and I call this as delta, the fattening of S. Delta, it's a positive real number. Okay, after all this, recalling this topological notion, let me point out some facts. So, in general, we have that a set is contained into its closure, but if I take these balls, which correspond to add some noise delta to a set, I cannot distinguish between a set S and its closure. So the point is that when you have noise, it makes no sense to distinguish a set from its closure. So I will move to the complete lattices of closed subsets. The other thing is that the closure of a set is actually the intersection of this flattening. So the idea is that if you reduce the amount of noise, making arbitrarily small, at the end you will get the closure of S. And now one can define a notion of robustness, which is at the level of monotonic maps between complete lattices of this particular form. So here I'm assuming that these are metric spaces. These are the complete lattices of closed subsets. And I say that a monotonic map is robust at a certain point if for every small epsilon there is a delta. So if I make, basically what he's saying is that if I want to get an approximation of A of C up to epsilon, I have to have a good approximation of C at least up to delta. That's the intuition. Okay? And again, if the space, the metric space is discrete, every monotonic map is robust. So this notion is not interesting in a discrete setting. Okay, so now let's go back to reachability. So I've shown you that given an hybrid system, I can define a transition relation. So I'm back to the standard setting. So I can define, given a transition relation, this reachability map exactly as before. It's not really relevant whether S is Euclidean space or metric space or something else. The main problem is that this definition, if you take a transition relation corresponding to some hybrid system like the one modeling the bouncing ball, fail to include zero points. So it basically says that the ball will never stop. You don't reach the state when the ball stops, which of course it's false. You know that it will stop. So the first fix to solve this problem is to replace arbitrary subsets with closed subsets. In this case, we get what I call safe reachability. It will include zero point. And the intuition here is that you consider reachable everything that is arbitrarily close to things that are reachable. That's the intuition. But by doing that, you could also add points that are not really reachable. For example, if you have some quantity that decays exponentially, so it goes arbitrarily close to zero, but will never reach zero in a finite amount of time, you will include, by taking closed sets, also zero as a reachable state. So by moving to this, we get something safe, which is okay. We get an over-approximation, which is acceptable from the point of view of safety. However, we have still a problem. This safe reachability is unstable. So if you make a bit of noise in this set of initial states, you may reach a lot more than what you reach by just starting from I. Now, before solving the stability issue, let me consider the fact that after all we are interested in hybrid systems, not in topological transition systems. So I'll define another complete lattice, which I call HC of S, which is the complete lattice of closed hybrid systems. That means that the flow relation and the jump relation are closed. So the idea is that I want to consider stability not just with respect to the initial condition, but also with respect noise at the level of the system. So I'm saying that imprecision could be also in the modeling of the system. Okay? So for that reason, if I take this complete lattice, I end up with a complete lattice of closed subsets on another metric space. Then there is this abstraction function, which is the function that, given an hybrid system, gives you the transition relation associated to it, the transition system associated to it. I should stress that although this is closed, the transition relation may not be closed. Okay? So a closed hybrid system does not necessarily lead to a transition relation which is topologically closed in this metric space. So now we can define safe reachability for closed hybrid systems. And then you can ask, is there, so there is another step that maybe I'll skip here. So now you can ask, since everything here and here could be viewed as, so also this one could be viewed as a complete lattice of closed subset of a metric space. So I can ask whether this map is robust. And robust means that it's robust both with respect noise at the level of the hybrid system and at the level of the initial conditions. Of course, in most of the cases, actually, usually it's not robust. So we don't have stability. Is there a way to make it robust? The good news is yes, there is a way. So let me define what it means to have a robust approximation of something. So as I have an analysis A, which could be my safe reachability analysis, but this definition can be applied to any monotonic map. I say that another monotonic map B is a robust approximation of A if it's robust at every point, and moreover, it computes an over-approximation of A of C. Of course, if you take the reverse inclusion as partial order, will be the green stuff, but it doesn't matter. Now, the good news is that under some assumption of on the metric space and S prime, every monotonic map has a best robust approximation. And the condition is that these have to be compact, compact subset. Should I recall the definition of compact?
Yes, please.
Okay. Maybe I can just give an example. So in the case of Euclidean spaces, a compact subset is closed and bounded. So it means that it cannot contain points that are arbitrarily far away from the origin. Okay? So if you have this assumption, then every monotonic map has a best robust approximation that I call it in this way, because dotted square. And actually there is also a simple way of computing it. It's just the intersection of the non-robust map applied to this fattening data, and then you take the intersection. Now, the proof of this result relies on the fact that, in general, on these complete lattices, there are three topologies that you can consider, and in general, this is the relation between these three topologies. There is the Scott topology, which is a topology that is defined purely in terms of the partial order. There is the robust topology, which captures the notion of robust map, and another topology that is called apperviatoris. When S is compact, these three topologies that usually are different, they are the same, and the thing that gives you the best approximation is the Scott topology, because that's order theoretic, and so somehow you always have the best Scott continuous approximation of a monotonic map, but that may not be so interesting, because if you are interested in robustness, Scott continuity is not necessarily the same. Okay? Warning, if the metric spaces are not compact, you don't have a best robust approximation. Even for something simple like the real numbers, there are maps, monotonic maps, that don't have a best robust approximation. Okay, so let me conclude. I would say that the main point of this presentation is that reachability analysis for hybrid system is not a trivial extension of what you do in the discrete setting. There are actually some issues about, so I try to be fairly general. So I started with reachability, but most of the notions that I introduced, they can be applied to other kind of analysis as far as they are expressed in terms of as monotonic map between complete lattices. Then, of course, one could ask, if I have an analysis, is it computable? Now, there is a notion of computability in the context of, not of complete lattices, but omega continuous lattices. And a precondition to be computable is to be Scott continuous. Of course, if you use this notion of computability. So somehow, taking the best robust approximation, it's a way towards ensuring computability, but it doesn't ensure computability. The other thing is that the gap between your analysis and its best robust approximation, it's a local property, it's not a point-wise property. So it means that it's sensitive to the metric space where your S lives. Okay? So if you reduce the space, but say you take a closed subset that contains your point, your set S, you may get a robust approximation on this subspace, which is better. Okay? So you put more constraints. The other issue is that I have this nice result about best robust approximation under the assumption that I'm working on a compact subset. Now, what are the compact subsets in the case of a Banach space? Now, if it's finite dimensional, so it's basically an Euclidean space, they have fairly natural things. So they are closed and bounded. Now, bounded in this context means, in the case of an hybrid system, means that you cannot go too far, and you cannot, your speed cannot be too high. That's what it means at the level of the flow and jump relation. Unfortunately, if you consider infinite dimensional Banach spaces, which could be useful to model certain kind of physical system, the compact subsets are not very interesting. They have empty interior. So that's it.
So, is there any question? No?
Then I
So we thank you, Professor Moggi.